Matrix multiplication somehow combines two matrices to produce a new matrix. This video introduces the rules of matrix multiplication. Given how important matrix multiplication is, we'll also understand it from different perspectives. Geometrical, from inner product, outer product, linear combination. We'll talk about them in the coming videos. Let's say now we have two matrices, A and B. Matrix A has a shape of M times P, meaning it has M rows and P columns. Matrix B has a shape P times N, meaning it has P rows and N columns. The product of A and B, denoted as AB or A at B, will be a matrix of shape M times N. From the perspective of shape matching, matrix multiplication AB requires that the number of columns in A equals the number of rows in B. Otherwise, multiplication cannot be performed. In the product AB, the number of rows come from A, the number of columns come from B. The matching dimension P effectively cancels out. A very good way to remember this is M times P at P times N, the middle dimension P is cancelled. Now let's see how to actually compute each entry of the matrix C, which is the product of A and B. The ij entry of C, called Cij, is the sum of the products of corresponding elements between the f row of A and the jth column of B. You might notice that row vector A at or times column vector B is itself some kind of matrix multiplication. A row vector A of shape 1 times P times a column vector B of shape P times 1 gives 1 times 1 matrix. And a 1 times 1 matrix is really just a single number, a scalar. So simply put, row vector A times column vector B is simply a vector inner product. That means computing A times B involves performing M times N inner products, one for each entry. Now let's talk about a very simple example. Matrix A has shape 2 times 3, matrix B has shape 3 times 2. So the result A times B gives us a shape 2 times 2. Looking at the shapes, in 2 times 3 at 3 times 2, the 3 in the middle gets cancelled, leaving 2 times 2. Now let's compute each element of A times B. Firstly, let's compute the element in the first row and the first column of AB. Next, let's compute the element in the first row and the second column. Then compute the element in the second row, first column. Finally, compute the element in the second row and second column. One important thing to remember is that matrix multiplication is generally not commutative. On one hand, even if A times B makes sense, follows the multiplication rules, it doesn't mean B times A will also be valid. Even though sometimes B times A also is defined, it doesn't mean that A times B and B times A will give us the same result. For example, in our case earlier, B times A will produce a 3 times 3 matrix, while A times B gave us a 2 times 2 matrix. Clearly, they are very different.